virus is not really programming intensive. The focus is really on trying to understand the algorithms. We've had, I think, at this point, if you've been following, you have a pretty good understanding of the worst case behavior of these algorithms, which is fine. That's great. It's important. It's kind of like in terms of solid information to convey. That's kind of what we have. But it's a different thing to talk about the average case in practice on a particular problem. That's a whole different thing. I don't have a lot of theory to give you on that, but you'll actually get some hands-on experience with that in a particular domain in this lab. That's the intent. All right. So hopefully what you find online will line up with what I show you here. But there's a lot of different files in that zip archive. So get it and unpack it. And I'll follow my pattern. I want to first give like the official assignment. Let's talk through that. Then there are some slides. Then there's a bunch of code, including some demos. Let's just kind of work through it as best we can. And I think the hour will probably fly by pretty fast. Will we possibly get all the way down to the ant's whisker view? All right, so for the main algorithms covered in class, there's the whole list of them, including A-star search without closed lists. Answer the following questions for a specific pathfinding domain. Okay. How does the average solution cost, computation, and memory performance of the systematic search algorithm scale with problem size? So the exact same question, except we're asking what you actually see in practice on average for a particular domain. Yeah, I am giving you a domain that's in that code, which I presume most and probably all of you will use, but you're not obligated to do that. If you have something else, you have other ambitions, that's possible. You will need to pick a particular domain where you can do your pathfinding. Compare the performance of each algorithm in practice to what is known theoretically. Right now, in practice, right? That's the average versus the worst case behavior. That's what I'm asking you. Do your best with that. So this is great, a great exercise. And it's much harder than it looks as a sentence, right? Because the theory is this weird big O stuff, and then in practice you get a bunch of data. Okay, and putting those two together takes some real insight and some thought and some work. Yeah, which algorithm is best to use on your test domain if the solution cost is our main concern, or if the speed of solution is our main concern, or if memory use is our main concern? Same kinds of questions, but with practical average case data. All right, now this lab may be kind of easy for some people, and if you want to make this more of a programming type of lab, you are welcome to try for the extra credit, or just maybe use your own pathfinding domain. That will be much harder than the minimum amount of work here. And what you could do for extra credit, what's suggested here, other than another pathfinding domain, which is clearly allowable as well, is to do something other than pathfinding using the code that's provided. That will make you dig down and understand the code probably better than I understand it standing up here. I wrote every line of the code, but 3, 4, 5 years ago. So you'll have to really understand it to do that, but it's doable. I've done that. What I'm saying, I know it's not a crazy thing I'm suggesting here, but it's much harder. So it's not the most efficient way to gain points for the class. That's what I would say. It's just like if you want to do that for your own benefit, and then by the by, okay, yes, I will give you a couple extra points. All right. Present your results in the form of a lab report with the standard 4 main sections as in the previous lab. Review the lab 0 slides, that last slide that goes and says what's supposed to be in each section if you need to. You will be graded based on how thoroughly and convincingly you answer the questions above. The document should stand alone and be largely comprehensible to other AI or M&S experts, even if they had not taken this specific class. And I make some comments about that below, so you'll see the kind of thing. I don't want you to lean too heavily on the fact that, we've been saying stuff day after day in this lecture, so I don't need to say any of that again. Well, the minimum amount you should say in your report. Okay. So you may make use of the provided algorithms and domain. You don't have to, but again, most or all of you will do that. And that domain that I give you is minimum travel time pathfinding, not distance, but travel time path planning on a grid. Okay. And that grid contains terrain, which is either go, where you can move full speed, or slow go, which is defined as you can move only half speed there, or no go, terrain that you can't enter at all. Okay. With movement in cardinal directions only, that means north, south, east, west. No northeast, no southwest. The code may be altered or replaced in any way desired. If you choose to use the provided code and domain, you have to take responsibility for their limitations and document your work correspondingly. That's kind of what I mean. When you write your report, yeah, you'll see some of the specific things I asked below. You might think aren't necessary because we've been discussing this topic in class, but I would like to see your view. I'd like to see you make a statement in your lab report. Okay, you may submit materials in addition to the lab report, such as a spreadsheet of raw experimental results. In fact, I suggest that you probably do want to do that. Sometimes you do end up doing a lot of work that really doesn't make it into the lab report, in which case you could like add a sentence about that in the lab report and put that work in the spreadsheet. But I usually try to avoid looking at the spreadsheet. I try just to consider your lab report, as with your thesis. Whatever additional stuff you have that doesn't make it into the thesis document, no one's going to have that, 3 years from now when they go and try and understand what you did, because it's some company trying to make a product that does something like what you did. This won't be available. Okay, so your report should include these items plus whatever else is needed. So these are things that I think I would really like to see in your lab report. So I'll be looking for them. Again, what will you use as a measure of problem size? This is the same issue we tackled in class, and you may want to tackle it in the same way, but just state it in your own words. That's it. Okay. Don't just assume. We've talked about it in class, and I'm doing the same thing. Therefore, I need to say nothing. No, you say the minimum. Okay, what will you use as surrogates of computation, i.e. time, and memory use? Again, we've talked about that in class, and you might be doing the exact same thing. I understand that. That's what the code is kind of set up for. Okay, but still explain. Plots of mean resource use versus problem size are a good idea. I will be looking for those. Include error bars. Okay. Setting the scale on the y-axis to be logarithmic is smart if you are expecting exponential scaling. Okay. So what I'm talking about here is if you expect this to be the law, right, which you might, based on the worst case performance, one hypothesis would be, hey, average case might be better, but it might still have the same general shape. Okay. I think that might be true in some cases, at least some cases, maybe all. Okay, if this was the case, and it's what I'm expecting, rather than going in Excel and just plotting X versus Y, right, and then you get these exponentials, you saw the dangers of that, like in my last presentation, right? That you get a bunch of different exponentials, it's really hard to see them on the same curve because most of them will look flat and you only see one of them, okay? But if you use a log Y scale, right? We take the log of both sides here, right? The log of y equals, when you take the log of an exponential, the x comes down, right? So the log of y is x log a. Okay, so now what have we got? If I'm plotting x versus log of y, what's the shape of the curve? Is that hard? If I'm plotting x, what's one of my variables? My other variable is log y, not y, but log y. What's the shape of the curve? It follows as I have it here.
If y equals a to x, then you get a linear.
Then I get a linear shape. Yeah. In fact, this is the practical way we test when you're expecting exponentials. You do this and you see if it looks linear, you're like, okay, it doesn't have to be perfect, but if it looks roughly linear, you could be like, okay, what I said was reasonable. Additionally, you can figure out from that what A is. How would you do that in practice? What's the slope of that line going to be? Nick says it's a line. Nick is right. And what's the slope of the line? Log A. So you can go and measure the slope or, get Excel to tell it to you in one form, take its, inverse log, and you will have A, right? Again, if your theory is telling you that should be B to the D, worst case, and you wanted to compare to that, now you can kind of directly compare, right? It was B below. Well, what is B for this problem? I'm not going to tell you. Think about it. What is B for this particular problem that I'm giving you? Okay, is A B? Is that is that what as it would be for the worst case, or is it just some unrelated concept? Okay, I've yet to see. This is something that's I think may actually be a little bit of a challenge for you guys, but I think should be well within. Hopefully, I'm coaching you guys better than previous classes, so maybe you guys will get over the bump and be able to do something with those slopes. Okay. Yeah. All right. Anyway, generate the plots for sure. That's easy, and then do what analysis you can. Okay, that's it. That's the whole assignment document. Any questions at this point?
I think I'm just having, I'm just opening up the zip file. That's obviously all the code. I'm just trying to figure out how to set it up to run the.
Oh, we're going to talk about it. Practical stuff. We're going to get to.
Okay.
We still have PowerPoint and code to look at. So, all right. So let's look at the PowerPoint. So the PowerPoint is not fun, but it's maybe more fun than reading all the code. If I just said, "Oh, here's a bunch of code. Read the code." Be fair, but I'm not quite doing that to you. I'm going to give you a little bit of guidance here. All right, so this kind of shows there's a bunch of this is JavaScript, okay, and we'll probably be Python for labs 2 and 3, but this one's JavaScript. It should be okay for you guys, hopefully, especially because this is not. You can pick how programming intensive to make it, and by default, it is totally not programming intensive. Okay, this is kind of the main file that we use to run, and then there are. You know what? Let's run it. Let's run it before I get into the code, because it'll be hard, I think, to stay motivated where you see something. Now, it's not exciting when you run it. Don't expect graphics. Okay. When you run it, okay, you get this button. Copy CSV to clipboard. That's it. It ran. You can copy the results to the clipboard. Okay, that's it. So unless you go into Excel, which I will now go into and paste it. So I just did this a little while ago, so that's why it's already there. Okay, now when you paste it, actually, maybe I should do it again. Let's make another sheet. Let's paste it again. Okay, you will see that you want to do some processing on that. It's just a couple of strings. So when you get this special processing thing here, go and ask to use the text import capability and separate by commas. Okay, and if you then finish, now you will see things are split out pretty good. Okay, and this is BF is best first. Look. Okay, it's doing cost and memory the way we did it in class, which probably is what, again, most or all of you will do, but you don't absolutely have to. There may be other surrogates that are just as good. This is like wall clock time, right? That's what CPU is. So this is compute. This is memory. This is cost in terms of the cost of the path. How quick is it to get from point A to point B? And you can compare. And there's many columns because there are many algorithms. Okay. So this is what it does by default. Okay. And now you can go in and you can mess. The size parameter that I'm using here is the dimension of the square so it's a square matrix of terrain. And its dimensions is a 3x3 matrix. I think you're always going from one corner to the opposite corner. I forget where's the starting point, where's the goal. Okay, but
you can set the size like 10 and it's
yes, and you can do multiple replications. It's all set up for that in the code. I'll show you in a minute. Okay. All right, so that maybe orients you a little bit and I bought myself a little bit of patience to talk about this stuff here. So So this is like the top level, right? There's the JavaScript in there that's actually doing the top level stuff. What it's doing is it's invoking the path finding algorithms, which rely on this basic search code, which uses way down in the weeds here, uses this is our processing list. It uses a doubly linked list. We all know what doubly linked lists are. Oh, joy. Okay, use a doubly linked list. All right. Okay, and there's additional support files here. When you get to the end here, you really see all the really important files other than the demos. Resend Twister, that I don't know if you heard about that. You will when you get far enough with Arnie. That's one of the standard high quality random number generating codes, right? So you might be aware, any programming language lets you go in and ask for a random number between 0 and 1. That's the minimum. They will all do that. And they will give you the crappiest possible random. I mean, they're good for a game, but they're really not great for any kind of serious use. Okay, so even for this, even for this humble lab, I wanted something better than that. So that's a kind of a industrial strength random number generator. And this actually generates the grid of terrain. Okay. So let's kind of work top down. Let's look at some of the demos first before I go through this. I think it's the demos will help, I think, keep us motivated here. Let me sort by type. Okay, you can see there's a bunch of things here. So should I work? Let's do the terrain demo next. So if you do the terrain demo, again, you got to open the console to see anything. Here you can see a grid of terrain where the G is the good or go terrain and is no go, S is slow go. Okay. And you're trying to go again from one corner to the other corner, probably upper left to lower right, I would guess. Right. Initial state, final state. Plot a path. Give me the best path. Okay. Let's look at. Oh, okay. Algorithm details. Okay, we should maybe end up there. There's another demo here, just so you know it's here. This just does nothing other than test the doubly linked list. So this is not very informative unless you actually open the code and see what was pushed onto the list and what was pulled off. It's a pretty fully, so it's completely coded by me, but it's reasonably fully fleshed out. It allows you to do things like add things at the beginning of the list, add things at the end of the list, and also add things in terms of an arbitrary cost number, because we know algorithms that like that. Now, in fact, the way I've coded all of the algorithms is they use a cost number. I'll have a little more to say about that in a moment. Even breadth first or depth first, which normally you don't think of as maintaining a sorted list. Okay, but you can think about it that way. And I hope to convince you of that. All right, let's finish the grand tour of the code, then we'll look at the actual codes. Okay. Okay, so if you look in Lab 1 HTML right at the beginning, you'll see that there is an array of dimensions there. And that is the map sizes that will be run. Right now, it's just one, size 3. Okay, you probably want more than that. You can say how many runs you want for a number of replications per map size. I think it's fixed that you will have the same number of replications for all map sizes. The code's just all waiting for you to go say what your will is, and you could so the minimum path to generating the data is really, really short. Okay, if you just do things nominally. And as a general rule, I mean, again, just to say my philosophy. So I mean, I like to provide some. So usually in a moves cohort, we don't all come in with the same amount of programming expertise. We don't all take to the programming equally easily. So I like to try to make a path where you can get through it without doing a ton of programming. But I'm not trying to discourage people who want to do programming from programming. I try to give hints where you can do some more if you feel like it, if you have time for a particular lab. Okay. All right. So summary of lab1.html. So for each replication, it generates a map of the size that one of the sizes goes through them systematically. it checks that it's soluble. It actually does an extra run of A star just to quickly check whether it is a soluble map, because you could have like no go all up the middle, right? And there's no way to get from corner to corner. We don't want those. We want maps where it's actually possible to get from point A to point B. Okay, then it runs each algorithm as defined in one of those files, the pathing.js. For example, but best first search is run on a map terrain by invoking a function that looks like this, BFS. Here's the terrain, and then verbose is it's just a switch. And I want spam me with all kinds of additional details because the code isn't, because either I'm trying to understand it and I don't understand it, or I suspect there's a bug, and so I'd like to see some more details about what's going on. Okay? Normally that's left false. And then the results come out as comma separated values that you can easily paste into Excel. Good? Okay. All right, so pathing is like the top level algorithm function. So it's not pathing, as you know, that's a special kind of search. So this is the stuff that's specific to pathing. It contains, so for each kind of problem you want to solve with a search algorithm, you have to construct the search node, right? I mean, that because there's stuff like cost, and you've got to say what the costs are for your own problem. You've got to say what the states are. You've got to say for any given state what children can be generated from that state, the successor function, right? Now this is all in there. But if you go and do like the extra credit where you go and try to do your own domain or the 8 puzzle or something like that, you've got to define all this stuff from scratch. Okay. Top level algorithms. All right. You can create a starting path state that consists of the starting location only. What else would it be? You have to define cost. So yeah, it's not necessarily H cost. That would be for what? Like for a greedy search or something like that. I don't know why I said H cost there. Yeah, and then it says not used by all algorithms. Okay, so what I mean, this is just very confusing. Maybe I wrote this before I did the last implementation, because currently I actually do use a cost, and that's explained later on. Like, what sense does that make for algorithms that normally don't use a cost? But anyway, you need to define your cost. Okay, you don't need to do it for breadth first or depth first or whatever. I've done it for you, and it certainly would be possible to write search nodes that don't use a cost, because the doubly linked list can let you push to the beginning of the list or to the end of the list. That's all you need for breadth first and depth first, right? Okay. So yeah, I think this is more confusing than it needs to be, but hopefully you get the gist, or you will get the gist. Okay. Now you need to encapsulate whatever the starting path state is with a search node that's specific to your algorithm. Right? The algorithm specific node knows how to assign the cost numbers to each child. As to place the children in the correct position on the agenda. Okay. It also makes children using the algorithm specific search node. That would be your successor function. Okay. Now, the way this works, the way the code is organized at the end of the day, whatever algorithm you're running, you use one function to run the algorithm. It's called run algorithm, right? It's just that you run it with different search nodes, and that gives you different search behavior. Okay? All right. When you invoke run algorithm, so it goes down out of the pathing file and goes into the search file, which I'll talk about next. And it says, okay, do a search. Here's the search node. Here's an agenda to use. You give it an empty agenda, an empty processing list, doubly linked list in this case to use. I don't know what those extra Booleans are. And verbose, that is a Boolean. That's obvious, right? Say a lot or don't say a lot. And there we go. And then it uses the search nodes produced to find the resulting path and travel time, and we're done. Okay. Now, again, how important is it to understand all of these details for this? It's not super important. It depends on you. It depends on what your ambition is. If you want to make your own pathfinding domain to do, this is all pretty important. And I don't want to block people from doing that, so I need to say this stuff. If you're going to be kind of happy to use what's there, that's fine. But hopefully you still want to understand some amount of what you're running, not just, oh, it's blind faith. Professor gave it to me. Must be good. It isn't always. I try, but it isn't always. All right. Okay, so the next file is search.js. Okay, so this is generic kind of search algorithms. That's what goes on in this file. Okay, parent class for search nodes and a search function. The search functions designs internal function called step that does one pass through the algorithm, which we all know and love, right? Pull a search node from the processing list, goal test it, successor function, circularity, all that stuff. That's what the step function. Oh, it actually said, and there it is all broken up at the end. Yeah. Okay. 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 All right. And again, the search needs the processing list. This doubly linked list class is our processing list. So it's an ordered list. It's meant to be an ordered list. You give it an order function, which it optionally uses to sort your list by. And I always do that for all algorithms. I'll explain that on the last slide. Okay, the kind of methods, the smallest value can easily be popped from the list, right? That's this pop function here. It says when you do this, it returns you some data, the data that you put on the processing list. This is how you actually construct the doubly linked list. Here's your order function right here to map data to an order number, right? So that would have to be F for A star search. That would be G for uniform cost search, those things. And I'll explain the other algorithms in a minute. You can use this to check whether it's empty. This pushes to the head of the list. This pops, we already said. This pushes to the end of the list, unshift. That's a Python's name for adding to the back of the list, right? And then the add function uses the number and adds in numeric order. All of my algorithms use add and only add. Remove takes a cell out of the list. I don't know that. Well, I guess you might have to do that depending on what you're doing. All right. Now let me talk about the order numbers and what goes on here, right? So you produce a function that assigns order numbers to the nodes, and the doubly linked list uses the order number to decide where nodes go in the list, close to, at the very are they going to be the next one to be popped, or are they way in the back, or whatever? Okay. All right. Now, so I assign order numbers for all algorithms, including ones that don't traditionally use it. Okay, that was just to make it homogeneous. So it's easier to code for multiple algorithms when it's homogeneous. Okay, if it's breadth first search, what do I say with cost? Because again, there's no cost there. Well, you just make the cost of each child one more than its parent. Okay, that will force it to the back of the list, and that will make the behavior breadth first search. If it is depth first search, you make a child cost one less than its parent, including if it goes negative, it doesn't matter. Just one less than its parent, it will get therefore pushed to the beginning of the list and get popped earlier. Okay, and then uniform cost, greedy, A star. Well, these normally use cost. It's just the cost you would expect for those algorithms. Okay. All right, so that's the slides. Let's look at the simplest possible demo, which is not the main file that we actually ran. It's a file we have not run yet. So the main file runs all the algorithms. This one just runs one. So I think it's a little easier to look at. It's this one, algo details demo. Okay. If we go and run it, let's run it first. I have no idea what it actually shows, if anything. Let's run it. Open the console. All right, it can do that. Oh, okay. Looks like it's set for verbose or something here. Here's all oh my. Okay. Oh, generated some terrain and it's doing some stuff. Maybe we'll take a look at that in a minute. Okay, let's first look at the code that generates this. All right, so that's the whole file. It's HTML, so it's got all that extra verbose stuff there. Not a lot of JavaScript, as you see, to do a minimum. Hey, I just want to run this one algorithm. Okay, so let's track it through. So yeah, you see verbose is set to true here. It creates something called Twister, which is our new Merzen Twister random number generator. Here's the width and height for the terrain. Okay, generates that terrain and prints it out. There it is. Okay. All right. And then it says, let result equal depth first search on the terrain with verbose on. Okay. And then whoosh, it gives a result. We can't see the result. It must be way, way down there. Okay. All right. Now let's take a look at this and see if this makes any sense. The actual printing. I don't know if I can make sense of it. Let's try. Okay. I'm not sure. What is this object? This is a search node, I believe. You see, it's got a cost used to order the node. It's got a G cost in there. It's got its own is goal function, right? This is what you'd have to define for a search node, right? What's the goal for the 8 puzzle versus 8 queens versus Pathfinder? It's totally different. So that has to be on the user to provide these functions and create their own search node. So there is that function. It knows its parent node. Okay, so this is used when it actually gets to a solution, right? How does it actually find what the whole path is from A to Z? It uses the fact that each search node knows its parents. So when you have a search node, you get to the point in the algorithm, you goal test it. It says, yes, it's a goal node. I'm done. Okay, but what's the path? And now you got to go harvest the path by you go back to your parent, back to your parent, back to your parent, and you can connect the dots to see what your path is. Okay, that's the idea. Okay, so let's see. So it starts processing, notice that it's like column 0, row 0, upper left. Okay, cost 0. We've done nothing yet. Candidate positions are, it can try to move to column -1. That doesn't look promising. It can move to column 1. So this one, I don't know the details of how I don't think I'll be able to get there this morning, but obviously column -1 doesn't exist. So what's going on here clearly is what I'm doing to generate the children. So the way I implemented my successor function is I'm looking at adding 1 to the column, subtracting 1 from the column, adding 1 to the row, subtracting 1 from the row. And then I'm, as a second pass, going and saying, well, does that make any sense? Okay, here it doesn't make any sense, so nothing's getting added. Over here, it does make sense. So here we go. We got a new search node based on the new location. Okay, here's one, again, that doesn't make sense, so nothing's added. Here's one that does make sense, so it's another node going on the agenda. Here is a dump of the agenda, so we can see those 2 nodes on the agenda. You can see what order they're in. You can see it's ordering, here's the cost, it's trying to order them by the cost, right? It's doing, what do we say, depth first search, right? Children cost 1 less than the parent. The parent was 0, the children now cost -1. There has to be a tiebreaker applied here, right? Which is going to be, because those cost the same. That's the way it is with depth first search. Children go in the front. In what order? You have to decide that, or you just don't care and you just let the chips fall where they may. It's still legit depth first search either way. Okay, so that's what's going on here. All right, and then it reps off which one next? 0, 1. Okay, which one would that be? Okay, 0, 1 is this one. See the state inside that search node. So the ones on top in this case, unlike my illustrations of my slides and on the board, the one on top is the one that's going to come off when we pop. So here it is. It pops this off. Now it's trying to generate children again. Again, this isn't going to generate 1. This will, this will, this will. It generates 3 new children. Okay, and then there's the agenda dump, right? It had 2 before, 1 came off, and 3 went, well, how is it? I'm confused. Shouldn't there be 4? 1 came off, and these 3 should have gone on. Okay, here's the one that was there from last time. Look at the cost. And these, why are they not? Oh, one must have failed the circularity. One's going back to the initial state. That's what it is. Okay. So there you go. Total of 3 on the agenda. So you ought to be able to see, you can't, with some work, not saying it's totally easy, but with some work, you can dig through this and actually really see the details if you want. Okay, or if you need to, because maybe you're more ambitious. Try to do. Okay, if we get way to the end, let's see what the result actually looks like. It's probably, here it is. Here's the result. So the result that it returns, the algorithm returns, is an object. It's got the, must be, is it the length of the path? 3? Max length. Oh, max length is probably the max length of the processing list, I think. I think that's what that is. The total number of ads, that's the total number of nodes that got added to the processing list, which is not quite what I want for CPU time. I wonder if that's what's being used here. I'll leave it to you to criticize that. It's not doing the right thing. Travel time is infinity. What's that? Is there no solution? Let's go back up to the top and look. Oh, you can't actually get to the goal because it's bad terrain. Yeah, this lacks the pre-processing to check that it's actually doable. Okay. Yeah. All right. Okay. All right. It's most of what I wanted to do, but let's open up the main file that is the main file that's on the easy path to getting through the lab, just kind of using the lab1.html, and let's see how awful it is. Maybe we'll take a little bit of a tour of these files. Now it's a bunch of code actually in this directory. It's got, pushing 1,000 lines of code total. It's not totally trivial. You can see why I maybe stopped asking students to like generate this on their own. Because even if I made it easier and said, well, just generate A star, it's a bunch of work. It takes more time than we generally have. Okay, see this here? These are the widths of the terrain you want to use. So you want to if I want not just size 3 by 3s, but I also want 4 by 4s, then I would do 3 comma 4. If I want, 300 by 300, then I go with 3, change it to 300. Okay. And then how many runs per width? Easily changeable right here. Okay. And then down here, you see for every size of the terrain that you want run, it goes and generates the number of runs you asked for that, for that you asked to be done for each size. And then it keeps generating terrains. You remember the travel time was infinity when we failed, right? So if the travel time is infinity, it says, no, this isn't a good map. There's no solutions to this. And it leaves it aside and generates another one and another one and another one until A star successfully can solve it. Right? Okay, and then yeah, to actually run the get results from these things, look how easy it is, because of all the mess in the other files, it becomes very easy to actually go and run these algorithms. 1, 2, 3, 4, 5. There we are, all done. Iterative deepening down here. That's the whole deal. It adds a string containing all that stuff to the eventual output, and then just keeps repeating and doing all the runs you asked for. Okay. All right. Let's look at the next file. So this is the file that knows about pathing. Okay, so this is the specific path path search nodes. I guess 1 per algorithm, am I right? Yes. And see over here, like for breadth first search, right? The first thing you need to do is define a search node. Now, again, for JavaScript, it's weird. So constructors look like pretty much like normal functions, right? It's going to be used as a constructor. It uses some generic path search node that's in the search file. That's the generic search node. Whatever fields need to be in every search node, that puts those in there. And then you augment it. So breadth first search prototype is kind of your archetypical breadth first search node. So in JavaScript, that has to be an actual object. JavaScript is weird that way. It isn't like that in Python. You have to have an actual search node. When you have inheritance between classes, you need to actually instantiate the root class and have a specific member of that root class, which is kind of the root of your class tree. Okay, so there I'm creating that root. And then here I'm tweaking it to match breadth first. right? So like for breadth first, when to get the child cost, what does that function do? It gets passed in the G and the H and the F and the cost of the parent, and it ignores all of that except for the cost of the parent and makes sure that the child costs one more than the parent so that it gets boosted to the front of the list like breadth first requires. Okay, and then this is my make child function that actually makes a child search node that's legit for breadth first search. And that's kind of it. That's what that's the infrastructure that you need for breadth first. And same for depth. Depth first is comparable, uniform cost. Let's see if any of these is actually, they're like within a line of one another, all very similar, depth limited. Okay. And then this is the run alg. This runs all the algorithms. It's just what algorithm will it be? Well, what search node did you give it? If you gave it a breadth first search node, it's going to be breadth first search and so on. Okay. And you see, this isn't much. It relies on the search functionality in the search file, which we're going to in a minute. Uh, then this is the top level function. When you go and say, I want you to run breadth first search, give me the result. This is what happens. Okay, you give it the terrain, you give your verboseness, it goes and uses the search node that you just defined up above. It does a run alg using that search node, ta-da, returns you the results. Okay, let's look at the search a little bit. Okay, so what's in here? So here's kind of a generic search node here. You say got all of, so hopefully you've played this game before where you have a hierarchy of classes. If you haven't, you will, in Java at least for sure. And you basically anything you can make, right, just one time, put it in the parent class, that's a win. Save writing a bunch of similar code for each child class. So that's what I did here too. These are just kind of some, and it is pretty well commented, so you can kind of see. I'm not going to read it all now. I think that's too much. We've already had a lot this morning, a whole lot. So let's just finish a quick tour. All right. This is that search function that does all the heavy lifting. You can see how long it is. It's fairly long, but I don't know, 50 lines or something. I mean, not that bad. And you can definitely get through it if you care to. Okay. Right. And that's what's setting up for doing the standard algorithm, I believe. Here's the step function right here that does one pass through the algorithm. And if I wasn't tired and I didn't think you guys were tired as well of going through these details, we ought to be able to go through this and map this onto the algorithm. It's not that hard. Okay. What else we have here? Yeah, that's the important stuff. The doubly linked list should not be a ton of code. Um, Let me make a comment about this, actually. This is useful. So actually, if I were trying to make really hardened code for serious applications, I wouldn't use a doubly linked list probably for my agenda/processing list. I would probably use a something like a priority queue, which I've heard about priority queues. Um, so that's a pretty exotic data structure that's optimized to do exactly this task, to maintain a list in sorted order. It relies on a data structure called a heap. Anyone heard about heaps? I bet some of you have heard of heaps. You don't want to admit it, but you've heard of heaps. And that's like a subject for, like, if this was a CS, more of a CS curriculum than it is, we would probably have a whole class just to do algorithms and data structures side by side. But just so you're aware, so you do know what you need to do. If you were implementing this from scratch, you would probably not want to write your processing list yourself. You would be out looking for code out on the web, and you would see different approaches would give you big O information for describing what the memory and computation complexity is. Now, you ought to be smart enough at this point to make use of that, to realize that, oh, this priority queue thing, I don't know what the heck it is, but it looks good in terms of its complexity. Maybe I want to think about using that. Okay. All right. I think I'm going to leave it there unless there are questions. All right. So good luck to you on the lab. Let me know how you're doing. Remember, our next meeting will be Tuesday, right? Monday's a holiday. We'll be on that side of the barrier and it'll be 1100. Okay. Have a great weekend.